Hi, chemists, and welcome to week 9's work. This week, what we will be doing is we'll be looking at rate of reaction. Just to give you an idea of what's coming up over the next couple of weeks, we have 8 weeks remaining. We're going to be looking at chapter 10 extensively now for the rest of this the rest of this month. We're looking at rates of reaction in the first one, and then rates of reaction 2. We're looking at some online investigative practical work that can be used to investigate rates of reaction. And we'll be then looking at some revision exercises in preparation for your end-of-year assessments. End-of-year assessments will be taking place in the 7th and the 14th of June. And then finally, right at the end, we'll be finishing off a rates of reaction in the last couple of weeks before the end of the academic year. So the word rate is sometimes it's viewed with a little bit of puzzlement and mystery. I don't want people to look at the word rates and be scared of it. Rates. More often than not, you could, in your everyday language, talk about rates as being the speed of a reaction, and that's pretty much the term that's used at the top of your chapter, top of the page, which is section 10.1. But it's really, really important for us to actually talk precisely about what it is that is progressing in a chemical reaction. When we talk about chemicals, we are talking, of course, about particles, and sometimes there is a little bit of confusion when people talk about rates of reaction. They kind of think, well, if everything is happening at room temperature, then surely the particles are moving at the same speed. And that is a misconception. It's a misconception with the term rate. So we can generally refer to the speed of a chemical reaction as being quite fast, and sometimes we can express it as being quite slow as well. So there are a few fast instantaneous reactions that we have studied very recently. For example, the precipitation of silver chloride, which is the test for halide ions that you learnt with me last week. When you mix solutions of silver nitrate and sodium chloride, immediately you get a white precipitate. So precipitate, that means it's a solid that will not dissolve in the liquid that it is contained in. And that's a very fast reaction. It's not actually something that will take a long time to do. So that's a precipitation reaction. Now, if we look at a rather slower reaction, one would be concrete setting. So we have a lot of skyscrapers, a lot of buildings that are being built in and around the UAE at the moment, and that reaction is actually quite slow. We've studied cement and its raw material, limestone. So concrete setting is when you actually have a process where you're actually making a hard substance, and you use cement, and you use sand, you use gravel, and you mix it up with water to form concrete, and you then let it set, and it's a great material for us to build highways and buildings with. The reaction is quite slow. It will take a couple of days for the concrete to fully harden. And on the right hand side, you can see that there is rust forming on an old car. Now this is usually a very slow reaction. It will take years and years for the car in the picture to rust completely away. Poor car. But it's not always enough to know just that a reaction is fast or slow. Not in chemistry. In factories where they make products from chemicals, they need to know exactly how fast a reaction is going and how long it will take to complete. In other words, they need to know the rate of the reaction. Now, let's look at this term very, very clearly. Okay, exactly how fast the reaction is going and how long it will take to complete. There's a very clear indication that we are looking at an aspect of time. Okay, so somewhere within this, there has to be we have to take into consideration a unit of time. And sometimes chemical reactions take place within seconds. Sometimes it takes place within minutes. Sometimes a chemical reaction can take place and complete itself within hours or even days. So it's very, very important for us to make sure that there is some aspect where we're actually measuring a chemical reaction taking place within an hour or maybe within a second. We choose a time unit and we say this much chemical reaction has happened over this second. Now, say for example, if we actually we go back to our first example from the page where we have a precipitation of silver chloride. You can actually see that one of the liquids, it's silver nitrate for all intents and purposes. Let's say silver nitrate's at the top, and that's being added as a colorless solution to silver chloride. Now, as you add the silver nitrate, immediately you get a precipitation. But let's say, for example, that you have quite a low concentration of sodium chloride in that beaker on the surface. Now, as you add the silver nitrate, the silver chloride, as you add the silver nitrate, the sodium chloride will start to get used up. And it's precisely what we're talking about the chloride ions. So the chloride ions will bind with the silver ions that are being introduced to the solution. Now, as time goes by, when you add the silver nitrate to the sodium chloride, it gets harder for the silver ions that you're adding to find the sodium chloride. This is from two reasons. First reason could be that you are adding more liquid, so you're diluting the solutions, and so the ions are getting further and further away from each other, assuming they haven't paired up with each other. Second thing is that as soon as a chloride ion meets a silver ion, so a positive silver ion meets a negative chloride ion, immediately you form a precipitate. So that chloride has been used up. Okay, it's no longer part of the solution. So the concentration of the chloride goes down, and so it takes longer and longer for the silver ions to find chloride ions. So if, say for example, we have a certain quantity that are made right at the very beginning, later on in the reaction, it would take a longer time to make that same quantity. So if we, say for example, find that it takes 1 second to make 1 gram of silver chloride, at the start, it may take 10 seconds to make another gram later in the reaction. And that kind of leads on to how we determine speeds of chemical reactions in chemistry. So we need to know, we need to have a definition of rate. Okay, rate is a measure of how fast or slow something is. Now, in everyday examples, we're going to talk about planes moving 800 kilometers in 1 hour. So we would talk about the rate being how much has actually been covered, 800 kilometers per hour. Okay. Petrol pumps can pump out petrol at a rate of 50 litres per minute. So after 2 minutes, you'd expect it to give you, yes, 100 litres. This machine can print newspapers at the rate of 10 copies per second. So if a shop wanted to get a delivery of 10,000 copies of the Collegiate Times, I'll leave it to you to calculate how many seconds this printing service would actually take. So from these examples, you can see that rate, and this is a definition that you need to know, I will test you on this, rate is a measure of the change that happens in a single unit of time. Please make sure that when I ask you that quiz question, you put that definition word for word. Don't go off on Google. I know the people who love to do that. I know you know that I know you know I know. Right. So use the guidance, use the definition in your book. That is what Cambridge want you to be able to say. Now, you can say any suitable unit of time, second, minute, hour, even a day. Right, here's a chemical reaction. as zinc. Zinc and sulfuric acid. It's quite a slow reaction, I must say. The zinc disappears slowly, a gas is given off. Now, as time goes by, you get a big fizz at the start because all of the positive hydrogen protons that are inside the acid, they start attacking the zinc straight away. And as time goes by, those positive hydrogen protons are being used up. So there's less and less and less of them, and so you have less bubbles that are formed over time. So as time goes by, in the second picture, the gas bubbles off more and more slowly. It's a sign that the reaction is slowing down. And finally, you don't get any more bubbles appearing. The reaction's over. All the acid particles have been used up. H+ ions, positive protons. Some zinc remains behind. That's because the zinc is what we term in excess. There's more of the zinc than actually the acid particles that can react with them. Here's a lovely equation, a word equation to summarize that up. Zinc plus sulfuric acid forms zinc sulfate plus hydrogen, gas coming off its hydrogen. There's your balanced equation as well. Solid, aqueous, and gas. Both zinc and sulfuric acid get used up in a reaction. At the same time, zinc, sulfate, and hydrogen form. Now, what we could do is we can measure 4 things. We can either measure how much zinc is used up per minute, or we could measure the amount of sulfuric acid used up per minute. Now, both of those would give us an indication as to how fast the chemical reaction is going. If they're being used up very, very quickly, that means your rate of reaction is high. Or we could look at the products, the amount of zinc sulfate produced per minute, or the amount of hydrogen produced per minute. So if the amount of hydrogen is produced, that is a lot. If it's a lot of fizzing, that means you've got a huge rate of reaction. Okay, a lot of fizzing, lots of hydrogen being produced per second. When it's not fizzing that much, you've got a low rate of reaction. Not so much hydrogen is produced in that same second, in that unit of time. You can use second, you can even use a minute. So for these reactions, it's easiest to measure the amount of hydrogen produced per minute, since it's the only gas that's formed. It's very difficult to measure the amount of zinc sulfate that's being produced, for example. You'd have to use something that can precipitate with the sulfate and maybe use a colorimeter to see how much light can pass through. It's not a very easy study to do. The amount of sulfuric acid used per minute, you could track that using a pH probe. That is possible. The amount of zinc used up per minute is a bit of a tricky one, because what you'd have to do is you'd have to remove the zinc, stop the clock, remove the zinc, clean the zinc, weigh the zinc, measure the mass of the zinc, and then put it back in and then start the clock. It's not impossible, but it's difficult. In general, to find the rate of a reaction, you should measure either the amount of a reactant used up per unit of time. When we talk about the amount of the reactant, it could be grams, it could even be centimeters cubed if we're talking about a volume. So in general, to find the rate of reaction, you should measure the amount of a reactant used up per unit of time, or the amount of a product produced per unit of time. So we'll leave it for now, but remember that when we're talking about rate, we are talking about the rate of reaction. We're talking about the amount of a reactant used up per unit of time, or the amount of a product per unit of time. Rate is a measure of the change that happens in a single unit of time, and rate in our everyday language is kind of surmising exactly how fast a reaction is going and how long it will take to complete. And some reactions are fast and some reactions are slow. Thanks very much for watching this. This is an introduction. It's a nice, easy, gentle introduction, and I expect you from this lesson to just understand what the definitions are of rate of reaction and what you should measure if you are trying to investigate rates of reaction. Thank you very much for keeping it simple, because it is Ramadan, and I'm also aware that many of you have your end of year assessments in biology. So best of luck with those. I know my class has been set that as well. So now you can go off and, after you've done the quick quiz, and it's a very quick quiz, you can go off and do your prep for biology. Take care, stay safe, stay at home. Bye for now.